Okay, there are more normal approximations than we're going to cover today, but we're going to start with the normal approximation to the binomial distribution. It would make a lot of sense to approximate the normal distribution with the normal distribution. Okay. So if we remember, if x has a binomial distribution with n and p, then the expected value of x is np, and the variance is np times 1 minus p. So that's what we knew about the binomial. Okay. And if you know that, then the binomial distribution can be approximated by normal distribution with the same mean and variance. So what that means is you'll use a normal distribution, and the mean will be n times p, and the variance will be np times 1 minus p. And this approximation works well as long as you check that n times p is at least 5, and n times 1 minus p is at least 5. Okay. So for example, suppose that x has a binomial distribution with n equals 20 and p equals 0.5. So we could find the probability that x is less than or equal to 7 by using the binomial distribution. Okay? So this would be the exact probability. So x has a binomial distribution, so if I use the binomial distribution to find the probabilities, I'll get the exact probability. So to do that, for each x value, I would have to plug it in to this equation. So I'd have to do that for 0 all the way up to 7 and add up those probabilities. That would take a fair amount of time. Okay. Or you could use the normal approximation. So we'd find the probability that x is less than or equal to 7 using the normal distribution with a mean of np is 20 times 0.5, which gives me 10, and the standard deviation of the square root of n times p times 1 minus p. Okay. So we know that we have our mean of 10 and standard deviation of 2.23. So I want to find the probability that x is less than or equal to 7. I would have to standardize it by doing 7 minus 10 over 2.23. And again, remember the capital Phi just means that's the CDF for our standard normal, for our z variable. Okay. So when I do this, I get a probability of 0.08. So my exact probability is 0.13. My approximation is 0.089. Notice that's not super good at the moment. Okay, I'm not thrilled about that approximation. And so what we've discovered is if you want to use the normal distribution to approximate the binomial distribution, what you need to do is use the continuity correction. So to do this, instead of finding the probability that x is less than or equal to 7, we use the normal approximation to find the probability that x is less than or equal to 7.5. And I'll show you why in a second. So if I use 7.5 instead of 7, notice that now my approximation to the probability is 0.13177. And the exact probability is 0.13158. Notice those are very close. We're only off by a couple 10,000ths. Not going to make a significant difference. So we figured out that the normal approximation works very well, but it does work better if you use this continuity correction. So first of all, why do we need a continuity correction? So I've drawn in here for you a normal approximation to the binomial. So I've drawn the binomial is the lines, okay, and the curve is the normal distribution. Notice that it does follow this binomial distribution very well, but if you look in really close, notice how like right here, the line kind of overlaps the curve just a little bit. Okay, or like over here, it kind of overlaps just a little bit here, but it does seem to follow the curve very well. But you do have just a little bit of overlap. And so what we've done is we said, well, since this probability is just a little bit higher in some places, instead of finding the probability that x is less than or equal to 7, if I do the probability that x is less than or equal to 7.5, I get just a little more probability in there, and it just makes up for that little bit of overlap. Now, technically, you probably could have done the probability that x is less than or equal to like 7.4 instead of 7.5. That probably would have worked. We just picked adding 0.5 because it was a nice, even way to do it. And it seems to work very well in practice. Lots of times, so even though the binomial distribution is discrete, so technically we should draw it with lines, you'll find a lot of software that kind of draw it with the rectangles. And the reason why is when you draw with the rectangles, you can really see the overlap just a little bit better. So we're going to explore this applet. So here's a binomial distribution, and it will let me change n. Okay, so notice right now, okay, it's a binomial distribution with p equals 0.5. But I can change n. So right now, if I have n is 2 and p is 0.5, what is n times p? 2.5. So is that big enough for us to use our approximation? Okay, no, because we need n times p to be at least 5. Which is why when you look at this, notice it doesn't seem to follow the curve that well. But as I make n bigger and bigger, notice what's happening. It seems to follow that curve better and better, and if I get all the way up to like 50, notice it is almost exactly on the curve. So as n gets bigger, this becomes a better approximation. If we switch to this page, we can control our sample size and our probability. Okay. So right now n is 10, p is 0.5. If I multiply those together, I'm at 5. So that's big enough to use the normal approximation and have it be reasonable. What happens though if I start changing my probability? Notice as I change my probability from 0.5, my binomial is no longer symmetric. And notice that my approximation is getting worse and worse. So what if I change n to, say, 100 or 1,000? Okay. Notice even though my probability was small and it started off skewed, by the time I get n so big, I guess it will only let me go to 100, it's now a very symmetric distribution that follows the normal curve very well. And even though I change my probabilities, I move along, but it still stays very well with the curve. What happens though if I start getting really small? Okay, at 0.03, 100 times 0.03 only gives me 3, which isn't quite big enough to use the normal approximation. Or at p equals 0.01, then n times p is only 1, which isn't big enough to use the normal approximation, which you can tell because it doesn't quite line up there. So, just to kind of show you how it does work better if n times p is large. Okay. And you do want n times 1 minus p to be large as well, so like if p is 99, then n times 1 minus p is still only 1, and again it doesn't quite line up. So here's the more precise continuity correction. So if we want to find the probability that x is less than or equal to x, when we're trying to use the normal approximation, we find the probability that x is less than or equal to x plus 0.5 while using the normal distribution. Now, if you want to find the probability that x is greater than or equal to x, we need to find the probability that x is greater than or equal to x minus 0.5 using the normal distribution. So I always think of it as I'm adding on the 0.5 to be safe to try and make my region bigger. Okay? So if I was looking for the probability, here's my 7. If I want to look for the probability that x is less than or equal to 7, to make my region bigger, I would go to my 7.5. But if I wanted the area greater than or equal to 7 to make my region bigger, I'd go to 6.5. So you just always add on the 0.5 in the direction that will make your region bigger. Let's actually try it. So for example A, if x has a binomial distribution with n equals 14 and p equals 0.4. We want to find the probability that x is between 3 and 6 by using the normal approximation. The exact binomial probability, if you actually use the binomial formula, will be 0.65266. So we want to see how close we can get using the normal approximation. So first thing we need to calculate is what is my mean. Okay, so my mean, we know my mean will be n times p. So 14 times 0.4 gives me 5.6. And my standard deviation is the square root of the variance, which is np times 1 minus p. So square root of 14 times 0.4 times 0.6 gives me 1.833. And I guess before I start using this normal approximation, what am I supposed to check? Before I can use the normal approximation, I need to check is n times p, which is 5.6, that is greater than or equal to 5. And n times 1 minus p gives me 8.4, and that is at least 5 as well. So we've met our assumptions to use the normal approximation. We know our new mean and our new standard deviation. And at this point, we're just going to do everything that you would have yesterday using the normal distribution. But here's my 3, here's my 6. I want to find this area in between. Okay, what is my continuity correction going to look like in this situation? So I'm going to be interested for x between what two numbers? 6.5 and 2.5. So remember, in each direction, you want to go out 0.5 to make your region bigger. So we're going to find the probability that x is between 2.5 and 6.5. So that's my continuity correction. Now at this point, we're using the normal approximation, so we're going to use all of our normality rules. So we need to standardize. So to standardize, we take our first value of 2.5 minus the mean of 5.6, divide by the standard deviation of 1.833. So that will be less than or equal to x minus the mean over the standard deviation. Less than or equal to, and do it to my second value, 6.5 minus 5.6 over my standard deviation of 1.833. So z, because we standardized, so now we have z's. Z is between negative 1.69 and 0.49. At this point, what do I need to do? I need to go to my table. If I look up my 0.49 value, so 0.49, that puts me at 0.6879. So 0.6879, and then I find my negative 1.69. So negative 1.69 puts me at 0.0455. And if I subtract them, that should give me the area in between. So 0.6424. Notice we're not extremely close because n times p was pretty close to 5, so it was just barely in our, it's okay to do this range. But our approximation is still pretty close to our exact probability. If anyone wants them, I did have more normal tables up here at the front if you wanted to have one in front of you to follow along. Okay. So questions on that example 8. Now example 8, we probably could have found the exact probability without too much work. It wouldn't have taken too long to put into our calculator. But example 9 is when it really comes in handy. Okay. So in a test for a particular illness, a false positive result is obtained about 1 in 25 administrations of the test. So that means the probability of getting a false positive is 1 out of 125. Okay. If the test is administered to 15,000 people, so n equals 15,000. Estimate the probability of there being more than 135 false positive results. Okay. So this is a binomial because each test is either false positive or not false positive. People should be independent. Okay, the probability should remain constant, and we know in advance how many trials we're doing. So it is a binomial, but we're looking for the probability that there are more than 135 false positives, which means that you would have to do the probabilities from 135, 136, 137, all the way up to 15,000. Even if you try to use the common rule, you still have to find all the probabilities from 0 to 134. That's going to take you a long time, no matter how you look at it. So that's why the normal approximation is very useful. First, let's check and make sure that we can do it. So n times p is 120. So that's at least 5. So we're good there. And n times 1 minus p is 14,880. So that's definitely bigger than 5 as well. And because these numbers are so much bigger than 5, it's probably going to be a very good approximation. So at this point, we need, if we want to use the normal approximation, we need to know what our mean and standard deviation are. So my mean is NP, which gives me 120 again. And my standard deviation, the square root of n times p times 1 minus p. So the square root of 15,000 times 1 over 125 times 1 minus 1 over 125. $10.91. Anyone correct me if you get anything different? And at this point, now we just use the normal distribution like we learned yesterday. So to start with, I'm looking for the probability that x is greater than or equal to, or just greater than 135. So we're looking for the probability that x was greater than 135. So if it's more than 135, am I including the 135 in the binomial? This is really equal to the probability that x is greater than or equal to 136. So if this is my 136, I'm looking for the area to the right to be on the safe side and add just a little bit more into that region. Then I'm going to start at 135. So it's going to be approximately the probability that x is greater than or equal to 135.5 using the normal distribution. So we need to go through and standardize. So minus the mean, divide by the standard deviation. So z is greater than or equal to 1.42. Now when I look up 1.42 on my chart, so I come down to the 1.4, go across to the 0.02, I get 0.9222. But that is the area to the left. So what do I need to do to get the area to the right? Use a complement rule of 1 minus. What was it? So 1 minus 0.9222 gives me 0.0778. Okay. So much faster than finding all the probabilities greater than 135. So do you have questions on this? What is the most complicated part of doing this? Or nothing's complicated? Okay, we'll move on. So this next thing that we're going to learn about is the central limit theorem, and this is what I started to try and tell you yesterday and then realized I was a section ahead. So what happens now is if we have the x1 up to xn is a sequence of independent, identically distributed random variables. Now, independent, identically distributed comes up so often in statistics that we call it IID. Okay. What that means is they all have the same distribution, they all have the same mean, mu, and they all have the same variance, sigma squared. Okay. Then the distribution of their average is approximately normal. So this tells us that it works for any random variables. They don't have to start off normal, they don't even have to start off continuous. You take any random variables and you find the average is going to be approximately normally distributed with a mean and mu, and then we know that for the average, instead of the old variance, we have the old variance squared over the size of our sequence, so over n. So this tells us that the average of any IID random variables will have a normal distribution. So it doesn't matter, it can start off with any kind of distribution, and your average will have a normal distribution. This is a good approximation if n is at least 30. Okay. Now, if you start off with something that looks pretty much like the normal distribution, you're not going to need such a big n before it starts looking like the normal. But if you start off with something that's like really right skewed, or we haven't really talked about skewness yet in this class, if you start with something that looks like this, that's not very symmetric, it's going to take a bigger sample size n before we look like a normal distribution. And so that's our central limit theorem, probably the most important result in statistics. And we can also do it with sums. So this is the average, but you could do it with the sum. So like x1 plus x2 up to plus xn is going to be approximately normally distributed with a mean of n times mu and a variance of n times sigma squared. And again, that works for any IID random variables. So for this example, let xi be the strength of a chemical solution that has a beta distribution, which we haven't learned about the beta distribution, with A equals 18 and B equals 11. The mean is 0.6207 and the standard deviation is 0.0886. Use the normal approximation, or the central limit theorem, to estimate the probability that the average strength of 20 independently produced chemical solutions is between 0.6 and 0.65. So to start with, I drew you a picture, or I put in the picture of what this distribution looks like. Notice it's not quite symmetric, but it is still fairly bell-curved. Okay. And so we want to use the central limit theorem to find the probability that we're between 0.6 and 0.65, that the average is. Okay, so n equals 20. Notice that's not all the way up to 30, but because this started off fairly bell-shaped and fairly symmetric, a sample size of 20 should be good enough for me to use the normal approximation. Let's see, so we know our sample size. I need to know my mean. So my mean is going to be what? Let's see. So let's start with this. Okay, so the original mean was 0.6207. The original standard deviation is 0.0886. Okay, and we are interested in x bar. So if we use our symbols correctly, we can differentiate. So when I say the mean now, I want the mean for x bar. And the mean for the x bar, we know is just equal to the original mean, so 0.6207. And for the standard deviation, sigma is going to be the square root of our sigma for x bar is the square root of our old variance divided by n. So the square root of 0.0886 squared over 20. So my mean for my x bar is 0.6207, but my new standard deviation for x bar is 0.0198. We know whenever we talk about the means that my standard deviation becomes smaller than it used to be. So now we're looking for the probability that x bar is between 0.6 and 0.65. Okay. But we know x bar has a normal distribution, and at this point, do you know how to find this probability using a normal distribution? Okay. We just start by standardizing everything. So 0.6 minus the mean for x bar divided by the standard deviation for x bar. Okay, you will notice as I go through that I try to be careful as I'm standardizing this that I minus the mean of x bar and divide by the standard deviation of x bar. Okay. And then 0.65 minus the mean divided by the standard deviation. Once I've standardized, these are now z values. So I get the z is between 1.48 and 1.05, negative 1.05. And to find this, I'm going to go to my chart, look at my 1.48, so 0.9306, and then look at my negative 1.05, which gives me 0.1469. So 0.7837. Okay. Questions on that problem? Okay.
So we were adding up all the independent samples?
Yeah, we took the average strength of the 20 samples, so we added them up and divided by 20.
Okay.
For example 11, let xi be the number of cracks in a ceramic tile. So that means, and the probability that x equals x is e to the negative 1.2 times 1.2 to the power of x over x factorial. Use the normal approximation to find the probability that there are more than 750 cracks in 500 ceramic tiles. Okay. So first, what we need to do is, we didn't actually do any homework on the Poisson in this class, but if you recognize this was a Poisson distribution, and that means lambda is 1.2, and we know the expected value is just lambda, so 1.2, and the variance is again lambda, which gives me 1.2. Because before I can use this normal distribution, I need to know the old means and variances. Okay. Now, when we use the normal approximation to find the probability that there are more than 750 cracks in 500 ceramic tiles, okay, what does that sound to you like we're doing with all of our x values? Adding them up. So basically, let's say we have y is x1 plus x2 plus all the way up to x to the power of 500. Okay. And using the central limit theorem up above, it tells us that that sum of the random variables is going to be approximately normally distributed with a mean of n times mu and a variance of n times the old variance. Okay. Notice that works for any original distribution. Okay. So even though when you look at the Poisson distribution here, it's definitely not symmetric, it's not even continuous, it's discrete. Okay. But even though it doesn't look like the normal distribution, by the time I find the sums will be normally distributed. So we need to find the new mean. So the mean for y, the formula is n times the old mean. So n is what? How many united variables did we add up? 500, because there are 500 tiles. So 500 times the old mean of 1.2. So 600. And the standard deviation for y is the square root of n times sigma squared. So square root of 500 times, let's see, the variance was 1.2. So 24.49. So we have the new mean, we have the new standard deviation. We know that it should be normally distributed. Okay, using the central limit theorem. So at this point, now we can use everything we know about the normal distribution to find the actual probabilities. So we're looking for the probability that y is what? Greater than 750? It says more than. Now, of course, if we're using the normal distribution, it doesn't matter if I have a greater than or greater than or equal to. So we need to standardize it. So it's going to be y minus the mean of y divided by standard deviation of y. Again, it's important that you use the mean and standard deviation of y and not the original means and standard deviations. So it's greater than 750 minus my mean of 600, standard deviation of 24.49. This is a probability that z is greater than 6.12. Now, I go to the normal table at this point, and I look for 6.12. Notice how high does my table go? Only to 3.49, so 6.12 is somewhere way off in this corner. So that means the area to the left is going to be essentially 1, and the area to the right will be essentially 0.
One question.
Okay.
Why don't we have to use the like add 0.5 when we're doing these ones?
Add the 0.5?
Yeah.
Some people say you should still use the continuity correction with the Poisson. So you could do the add 0.5. Okay. At this point, though, because I am dealing with such big numbers, okay, so if I do 749.5 minus 600 divided by 24.49, so let me try that. So 749.5 minus 600 divided by 24.49 would have given me, I guess, 6.104 instead of 6.12. Okay. So I guess what I'm trying to say is, for any discrete distribution, you could use a continuity correction, but people usually don't bother unless it's the binomial, for some reason, just because we get kind of lazy. And if your sample size is bigger than like 30 or so, then again, we usually aren't worried about it very much, I guess. So you could use the continuity correction, and you would have gotten basically the same answer. Usually, we really care about the continuity correction if we have small n's, or it's in that section and we're being tested on it.
So then should we only use the correction if we're doing binomial, or if it's just like a really small sample size? Or
Yeah, so it's only important for discrete random variables to start with. So like we definitely wouldn't have needed it in example 10. Okay, for example 11, and technically it is discrete, so we could have used it, but the book doesn't talk, or your textbook doesn't talk about using it for the Poisson, so I didn't worry about it here. Other books might have, but again, it's not too big of a deal, so.
how small is small enough of a sample size? Like 20 and smaller?
I would probably say, to be safe, like somewhere between like 30 and 50 is probably when I would stop caring. Now that's just kind of me personally. Okay. As far as this though, just so you guys remember, I have taught you to use the continuity correction on binomial, so use it on binomial. For anything else, it's probably not going to make a big difference. Other questions on this section? So this is section 5.4, and it's distributions derived from the normal distribution. We're going to use all of these distributions further on in the class. Today we're just introducing their names and kind of what they look like. So start with, if we have a random variable x that has a normal distribution with mean 0, variance 1, then if you square that random variable, you get what's called a chi-square random variable that has 1 degree of freedom. So y will be distributed with a chi-squared 1 degree of freedom. So that's how we use the symbols. If you have, again, a lot of x variables that are normally distributed with a mean of 0 and 1, and you square each one and add them up, then what happens is you get a chi-square distribution with v degrees of freedom. So because I added up v of them, I have v degrees of freedom. We write this as w is distributed chi-squared with v degrees of freedom. The expected value is v, and the variance is 2 times v. Your possible x values are all x greater than or equal to 0, okay, or w's if your random variable is w. Okay, and this is what it looks like. So notice the shape depends on your degrees of freedom. So if we start off with like 5 degrees of freedom, okay, it's very skewed, it's not symmetric. V is 10, still not very symmetric. V is 15, getting slightly more symmetric, but still not very symmetric. So this is the shape of the chi-square distribution.
Is there a point where it becomes imbalanced to the right with like a large number of samples, like a large sample size, or does it just stay looking symmetrical with a large sample size?
It's still right skewed, just looking slightly more symmetric. Then we have the F distribution. So what happens for the F distribution is if you take two independent, they do need to be independent, chi-squared random variables. So chi-squared with its degrees of freedom divided by another chi-squared with its degrees of freedom. And you divide each one by its own degrees of freedom. So like V1 divided by V1. And you do that, you get what's called an F distribution. Now the F distribution is defined as having 2 different degrees of freedom. So it has degrees of freedom V1 and V2. Okay. And here are some nice graphs for it. Okay, so like this top graph line has equal degrees of freedom of 25 each. Okay. This middle line here has the numerator degrees of freedom of 5 and denominator degrees of freedom of 25. Okay. And again, when you look at this F distribution, it's still right skewed. Okay, and it has some different interesting shapes, and it depends on its 2 different degrees of freedom. As far as this class goes, like you will not need to memorize this, okay, how the F distribution is formed. Really, all that we'll do is we'll use the F distribution in our statistical procedures, and you'll just need to be able to look up probabilities on the tables. But we'll learn how to do that when we actually need the F distribution. The T distribution, what happens for that is you start with a normal random variable with standard deviation, mean 0, standard deviation 1, and variance 1. And then you divide by the square root of, you take a chi-squared random variable with v degrees of freedom divided by v, take the square root. So you do all that and you get what's called a T distribution. Okay, for the T distribution, the mean is always 0. Possible x values go from negative infinity to infinity. Okay. And this is what it looks like for different degrees of freedom. Okay. So at 1 degree freedom, we have this orange line. Okay. Then we move up to the purple at 2 degrees of freedom. 5 degrees of freedom is the blue. And infinite degrees of freedom is the black. Okay. Notice that the T distribution looks a lot like the normal distribution, but it's just a little bit flatter because we have a slightly bigger variance. Okay. And as v goes towards infinity, then the T distribution tends towards a standard normal distribution. Remember, standard normal distribution tan is a mean of 0, standard deviation of 1. And let's see if this applet will work. I didn't test it at home in Internet Explorer. No. Oh, there we go. Okay. Okay, so you can't see it all very well. This thing doesn't actually scale the applet. Okay, but the red curve is our t-distribution. Our blue curve is our normal distribution. Notice right now at 1 degree of freedom that my t-curve is much flatter. Okay, it has a lot more area out here in the tails. Okay. As my n gets bigger and bigger though, so let's go a little bit slower. Okay, so there's 3 degrees of freedom, 4, 5, 6, 7. Okay, here's 11 degrees of freedom. At 20 degrees of freedom, they're almost indistinguishable. By the time I get up to 30 degrees of freedom, okay, the two curves are very close. And if I get up to, say, like 50 degrees of freedom, it's hard to tell that there's a difference. So your t-distribution gets closer and closer to your standard normal distribution as your sample size gets larger.